Hi, and welcome to the first lab, an introduction to laboratory techniques and data collection. We'll learn about how to use some common laboratory gear, typically for volume and mass measurements and density measurements. We'll learn how to use it properly, the uncertainty inherent in the measurements we make, how to work with significant figures while making these measurements, and how to deal with the propagation of error that goes along with these measurements. Be sure to arrive prepared to this laboratory. Read pages 17 through 21 in your laboratory manual. That material will be on the next quiz. Bring the goggles that you purchased from the bookstore. Don't wear any shorts or sandals. Dress properly, please. Bring the laboratory notebook that you purchased at the bookstore. Make sure you've left the first 3 pages blank and you've included the 5 tables required for this experiment. I'd like to see the title, the date, the names, the purpose, and those 5 data tables. These need to be checked out before you can start, and it's to ensure that you're going to be working safely and show that you are coming prepared. To begin with, you'll hear this basic lecture, and hearing this first as a screencast should help. Okay, let's begin. You'll take measurements from 4 different containers that have water in them and measure them to the correct level of precision. If there are graduations, be sure to estimate a digit between the graduations. That'll give you the correct level of precision and also give you an idea of which container might be appropriate for a certain measurement. Some give higher levels of precision than others. Record the uncertainty level inherent in both, and take a look at page 18 for that. Now you'll have 8 washers, and we're going to measure some masses. So simply mass each of the 8 washers individually. 4 of them are aluminum, 4 of them are steel, and then calculate the density difference among them, the aluminum versus the steel. This should be straightforward since they have a roughly constant volume. They're all the same type of washer, and we'll assume a constant volume. Now it's time to transfer some volumes. So we'll tare a 100 ml beaker. This can involve either putting it on the balance and hitting the tare button so it reads 0, or simply having it read 0 and then write down its mass. In a crowded laboratory, you might have to do that. Find the mass of a 100 ml beaker and write it down. Record the temperature of about 100 ml of distilled water. You should find that, I believe it's the orange indicator in the sink, so I'll point that out to you. Record its temperature to the correct level of precision. Note that this is simply using a stick thermometer, and they do have graduations. Rinse a 15 milliliter analytical pipette with distilled water, and then drain all but the last drop from it. I'll demonstrate this for you. And that means it's ready to go. That little drop will give you higher precision when you actually transfer. Transfer exactly 15 mils of this 15 mil graduated pipette. You'll see that it has a graduation, and one graduation only, that indicates exactly 15 mils. The bottom of the meniscus should line up perfectly with that line. Transfer it into that tared beaker using the pipette. Since water has a density of just about exactly 1 gram per mil, we can measure the density of the water. We can measure the density of the water and figure out the mass. So let's see what it asks for. Repeat this 3 more times, and then we'll calculate the average volume of water transferred. We'll calculate the average deviation of water that was transferred. Take a look at your laboratory notebook. There's a section in that on deviation from the average. Okay, now let's measure some density. We'll take a empty pycnometer, and I'll point it out to you. It's shown roughly as this type of a container here, but it's something you probably haven't worked with before. We'll fill it with distilled water to the top of the narrow tube in the cover. We'll mass the full pycnometer, and the difference in mass should give you the mass of the water. We'll measure the temperature of the water as we've done before in the pycnometer using a stick thermometer. Use the correct level of precision. We'll calculate the exact density of the water by linear interpolation. And if you're not sure what they're talking about, it's straightforward. Just take a look at page 26. It has to do with the fact that water does vary in its density depending on the temperature. And if you have a table of densities at given temperatures, and you're somewhere in between those, you should be able to use that data to get accurate in-between data. That's the interpolation, and there's a sample calculation there. After that, we're going to remove the water, but there's no need to make it dry. We don't need to do that. We'll tear that drain pycnometer and leave on the balance. That means simply hit the tear button so it reads 0. Now you'll add that piece of metal, we call that a metal shot, and we'll record the mass of the metal shot. Since it's teared, that number that shows up should be the mass of the metal shot. Can you see how it didn't matter that the pycnometer was a little bit wet, since the only thing going in there and being measured is the mass of the metal shot? We'll remove it from the balance, and now fill it with distilled water. Note that some of the volume is now due to the metal. Mass the whole thing, pycnometer, water, and shot, and we'll clean it all up, return all the items to dry, and we'll use all this data to calculate the density of the metal. The table that you've created as you work your way through it should help you determine the density of the metal shot. Note that in here, some of the calculations, there's more than one calculation needed, so I'll show all the calculations needed. If there's no calculation involved, you don't have to do it, but if you had to do a calculation for part of that table, please include it in the calculation section of your laboratory write-up. Note that I've placed in red anytime it says calculate, so anytime you see that, that should show up in the calculation section of your lab report. We can summarize these results in a nice table. Don't forget to answer those post-lab questions. I always get a few students who do. That's worth a separate 5 points. Make sure you get each page of your laboratory notebook signed. I'll usually ask you to help clean up. Typically the balances get a little messy. And once that's completed, you are good to go. Let's answer some quick frequently asked questions. Should you work alone? No, we're working in groups of 2. No more, no less. How precise should those graduated measurements be? Don't forget to estimate a digit between the lines. That's called interpolation. If you are going to take a line and wonder where it goes beyond that, or even a curve, that's called extrapolation. If you're wondering about linear interpolation right here, don't forget that it is described in nice detail on page 26. And when you're recording the uncertainty of your measurements, if you're wondering what those might be, there's a nice table on page 18. The lab report will be due when you arrive the following week. Right at the beginning, we'll pile them up once we're a few weeks in. As you drop those off, you'll pick up the graded ones from the week before, and that's how we operate. Can you submit simply one report for your group? No, let's have separate reports. However, I don't mind if you work together when you write up your report with your partner. You guys should be in contact with each other. It's also a good idea to communicate with all the members of a lab. Everybody's performing the experiment. Scientists share information, so you can discuss your information with other scientists to see how valid you think it is. Nothing wrong with that. How do you avoid the common mistakes? Well, that's a good question to ask for your first lab, because these are typically when you will make them. So if you want to avoid them, read the common mistakes section on pages 14 through 15 of your laboratory manual. It's nicely outlined, the most common ones, and it's a lot of detail there. Also, if you want to write an absolutely awesome lab report, an ideal lab report is provided in the last couple of pages of the laboratory manual. So I'd recommend you read pages 10 through 11 and the ideal lab report on pages 101 through 103. A final note, you'll be graded in terms of 4 categories: W, C, A, T. Writing errors, that's typically typos, things like that. Calculation errors, that's either that your calculation is done incorrectly or it can't follow your work, you're not using canceled units, things like that. It's a common error for students not to show the intermediate work. I do need to see the canceled work. I love to see how you went about your calculation with a description too. See, well, when we get to the sample calculation, you can have a look. WCAT A is for accuracy, and that's determined by the laboratory coordinator, where for each answer you get, for example, your volumes here, there's a level of precision that we're looking for, and accurate, correct numbers. Points are taken off if you have the wrong data. NT is for your tables. In this case, there's 5 tables. They should be neat, and one of the common errors is that when you hand in the yellow copies on the back of your lab report, they get scrawled or in other ways undecipherable. So just be careful when you're writing to not write through more than 2 pages, and have a look at your yellow pages before they're handed in. Make sure that they are legible. Okay, here's a sample calculation. Suppose we're determining the density of water. Notice how a description is provided to make it clear as to what's going on. To determine this precisely, the temperature of the water was measured, since the density of water will increase with an increasing temperature. The temperature was found to be 22.3 degrees Celsius. We used the table on page 25 to interpolate this, and we find that the final density is 0.9977004 grams per mil. That is a lot of significant figures. This is the actual calculation. This is the description of the calculation. That's what we're looking for. One other thing, if the density of a metal as determined using the pycnometer is not making sense to you visually, this little visualization right here should help. Here's what you have before. Here's what you have after. The volume of the water that was lost through adding the piece of metal, they call it the metal shot, must be, in this case, 2 milliliters, since water has a density of 1 gram per mil, and it went from 25 to 23. That's a difference of 2 grams, 1 gram per mil, 2 mils. The density of the metal is mass divided by volume. Since we have 2 mils and it weighs 5.4 grams, that gives us an unknown metal with a density of 2.7 grams per mil, which is a match for aluminum. Your data, of course, should be far more precise. Okay, that's a little description of today's lab. We'll see you next week.